So we're looking at the man at 0 meters, which is at the origin of our observation, and the graph also shows him at that location. If I run the simulation, the graph will not change because he is stationary. So let's move him forward slowly and pause. So his position is at 5 meters, and you see him at 5 meters. And the position increased because this graph is going up. If I want to bring him back, I can bring him back slowly to the equilibrium position, and he waits. So when motion is forward, this position graph goes up. Well, forward. If motion is backward, this line comes back down because this is backward. That's how you see direction on a position time graph. It can also tell you how fast the motion is. So from this position, let's move him forward again, but this time much faster, and see what the graph looks like. So I moved him from 0 to 7 meters very quickly, and observe what happens to how steep the graph is. I moved him very fast, so the change happened in a very small amount of time. So in the first case, from 0 to 5 meters, this change happened in a time of about 2 seconds, from like 3 to 5 seconds. But now I moved him very fast, so the change happened in less than 1 second. So this is the part where he was moving much faster. This is the part when he was moving slower. What do you see about the steepness of these two graphs? You should see that the faster movement shows a much steeper line in the position time graph. So there's a relationship that we can deduce from the position time graph between how fast and what the graph looks like. We will get back to this. Case number 2, let's clear all this and bring him back to the -10 region, and let's add a velocity time graph. So now I'm going to show vector on the man's image, and I'm going to set the velocity to be 2 meters per second and run. So I paused. You see that there is a forward arrow, a small forward arrow shown on the man. You see that corresponds to 2 meters per second constant, unchanging speed. He's moving at constant velocity, which means the position is moving forward by 2 meters each second. So we see the position graph going up, which is forward. Well, yes, he is moving forward, and it is happening at a regular rate, which means this ends up being a straight line. If I change his velocity to 4, immediately you see that this arrow got bigger. So vectors are arrows, symbols that show the direction and size of measured quantities on paper. So this arrow became bigger when I increased the velocity. And this arrow went up, so the velocity of the man will now be forward 4 meters, so I expect this to continue from this point. As that happens, the man is going to travel faster on the image, and please observe what happens over here, because we just said the steepness of a position graph depends on how fast the motion is, and see what happens to the position graph when I increase the velocity. Let's go. Right, so you should observe that this line is steeper, in other words, has a higher gradient, or it has a higher slope than the first part. Well, this is where, you see, the speed was 2, and that's how steep it is. I doubled the speed. We saw the man go forward faster, the arrow got bigger, and this line on the position axis got more steep. Now, what if I want to bring the man back? Moving backwards means a negative velocity. So I can change this to say negative 2 meters per second. Immediately, you're going to see this arrow moving at the negative 2 mark, and the man actually turned back, and you see the vector is also pointing back. Since the man is now moving backward, we expect the position graph to come back down at constant velocity. Let's see. See, he's now at the origin, and he is at the origin. Position mark shows at 0. He is at unchanging velocity of -2. A minus velocity means moving backward. So here we had forward 2 meters per second. Here we have -2 meters per second. The speed is the same, but the direction has changed. So we moved at a slope of 2 meters per second in this region, and here he's moving at 2 meters per second, but the slope of this line would be -2 if you had to calculate. And you can see that this is a negative gradient and these are positive gradients. So this is where he's moving forward, and now he's moving backward. So let's change him to move at -4 meters per second and see what happens. We should see him moving back. Bigger arrow here, the -4 line right here, constant velocity. What do you expect to see in here? He's going to move back more quickly than this section. So it's going to look like this. A quicker change, and he is back where he started. So that's the velocity part. Now let's add an acceleration time graph and clear, so to see what happens at accelerated motion. I'm going to keep the man at the -10 position mark. I'm going to give him a 0 initial speed, so he's standing at rest. I don't see any vector labeled because he doesn't have a velocity, but this time I'm going to give him an acceleration of 2 meters per second, and I'm going to show the vector. So what I'm asking you to observe this time is, you see the acceleration vector is shown in green, the velocity vector is 0. I want you to observe two things. One, what happens in these graphs, and two, the directions of the velocity and acceleration vectors on the picture. So let's go. Since there is acceleration, now the man's speed is changing. The magnitude, the size of his velocity, by 2 meters per second each second, which means in about 2 seconds, twice of 2 meters per second, the velocity should have changed by 4, which is what we see. So this is saying the velocity is going to increase by 2 meters per second every second. So in 1 second, the velocity is reached up to 2. In another second, the velocity has increased by another 2 meters per second, so it is now 4. In the meantime, this graph, observe that this is not a straight line anymore. We will get back to that in a minute. Keep observing. Let's have him running for a little bit longer. And you see that he is accelerating. So I've run the simulation for 4 seconds now with an acceleration of 2 meters per second square. So in 4 seconds, the change in velocity should have happened 4 times 2 meters per second, which brings it to 8. So acceleration times the time gives us the velocity at the mark that we're looking at. And he has reached the position of 6 meters, which is where we see him on this graph. So all of these graphs are related to the story that we see above. What if I want to slow him down? What if I want him to slow down and stop? Which way do I have to push him? Would I apply the gas pedal or the brake pedal if I want to stop? Obviously, I apply the brake pedal. If a bird is flying forward to slow down, the bird would need backward wind. At least that would be the result. So a push backward would mean an acceleration backward. So let's give him a negative acceleration. So I'm changing the direction of the acceleration. Let's give him a big acceleration of -8. Immediately you see there's a backward acceleration while he's still moving forward. So he is moving forward and he's going to slow down and stop. And let's run. And that is what just happened. The acceleration is -8, so it's below the part that we can see. It's -8 constant. So this graph is now going down. Why? Because he was still moving forward, but he came back to zero. What is zero? Velocity is zero. So he's at rest at the moment. He has turned back. So, and he is at the 10-meter mark. Now, if I keep running, he is now a man at rest instantaneously, but still there's an acceleration backward, which means there's still a push backward. So when he was moving forward, the backward push slowed him down, and now the push continues, slowed him down to zero, as slow as he could get, and now the push continues, so he's going to accelerate backwards and see what that looks like. Let's keep going. And yay, he has reached a velocity that is now a negative value. We don't see the negative value here because it doesn't fit, but it is shown at the negative. So what happened was, the way we look at the velocity time graph, all of the values above zero are positive. What is positive? Velocity is positive. Any value below zero is negative. Velocity is negative. So on a velocity graph, any measurement up to this point in time, which is 5 seconds of our story, he was moving forward. What we did was we made him gain speed for the first 4 seconds and then slow down and stop for another second. All of this is moving forward. See, although this line is going down, this is not to mean it's going back, because this is velocity graph. If it's going down to zero, that means it's slowing down. But the value of velocity is positive, so it's still moving forward. This is the point where he instantaneously stopped. After this point, as soon as you go below time axis on a velocity time graph, you have negative values for velocity, and that's when it means he is moving backward. Now I want him to move at constant velocity at that point. I want him to continue moving backward, but I'm going to change his acceleration to zero and let him run. You see? He's still going back, but now with zero acceleration. So his velocity is not changing, but it is still a negative velocity, and his position time graph went back to being a straight line. I want to go back to this curve story that we observed before. In this first section, the man was speeding up. We can see that here the man is moving forward with positive velocities, and the speed is getting bigger and bigger and bigger, so he is speeding up. Earlier we said the steeper the position graph, the larger the velocity. Look at the change in the steepness of this graph in this first section. Please try to see that it initially starts with a small steepness. Well, initially it starts with a horizontal slope, which is zero. Well, yes, it starts from zero speed. And then it increases its speed a little bit. So the line should get a little steeper, and the steeper, and steeper, and steeper, and steeper. So the steepness of the position time graph means velocity. If velocity is increasing, the steepness should increase. Look at this second section. Now this is where it's moving fastest. So when it reaches that point, sorry, this is the point where it's moving fastest, and that's the section where we slow down, still moving forward, and stop right here. So now after this point, the steepness should be decreasing, and it gets less and less and less steep. So it's leveling out. The slope is becoming zero, and this is where it is zero. The tangent line is zero. So that is where the speed is zero.